All right. Welcome back, everybody. It's June 9th. It's nice to be back. Obviously, a lot going on my end. This is the smiley picture that we got of her. This is Kira. Yeah, she's doing great. Everybody's doing fine. But that means I have a lot of sort of backlog of stuff to talk about. So, and not all of it I documented all that well as I was doing it. So, not my best laboratory, but it's okay. I attended kind of like random stuff. I attended a webinar from Wingtra. So Wingtra makes a pretty cool vertical takeoff and landing drone. And they were talking a little bit about the new camera that they're packaging with. It's the Sony RGB61. And sounds like it's quite a bit wider view, and yet still like really good resolution, which should, the bigger the footprint of the camera, the longer, essentially the fewer passes you need to make. So the old camera is kind of up here. This is the Sony, I don't know, 6001 or something. And then this is the new RGB61. And so fewer passes means, you can basically image larger areas or whatever. So I'm interested. They didn't give a price on this. They never do. But I've been kind of interested in getting beyond the GoPros for a while. A comparison of some of the stuff that Lindsay and I did over the last semester has kind of convinced me that maybe the GoPros aren't doing quite as well. They're noisier than I thought they were. This was a neat one. I don't know much about this, but I'm just kind of mentioning this. This is the open photogrammetry format. Pix4D had a webinar on this, which I did not attend, but I just copied this from the email. I love that we've got maybe a push from the Open Geospatial Consortium to try to develop an exchangeable format for this stuff rather than everybody doing proprietary. And I was excited to see Pix4D adopting it. A lot of times these companies don't really have a lot of incentives to use open source stuff. So this could be a very good thing. I was looking at some of the last of the impervious surface stuff for Roanoke, and I found this spot in the town. So this is the buildings from a set of buildings from 2009, and then the same buildings from 2021. They painted the roofs white. This is a way to reduce cooling costs, especially on a big building. So pretty neat to see it. I don't know how widespread that was, but pretty cool to see one. I've been working a lot on getting the Busy Bee flying. So it had been flying, but I was changing out some of the components and redesigning some pieces. So this was a lot of work about 3 weeks ago. I probably spent 20 hours on this, kind of doing redesigns and reprinting and putting it together and all kinds of stuff. So this is sort of documenting that a little bit. I haven't pushed those up to like Thingiverse or anything. But a couple of the big upgrades, the Cube Orange is a newer model. It's like the Cube Orange Plus, which I don't know what else is on there. It's got the HERE 3 Plus GPS. I don't really know what we're getting out of the Plus, except it has 2 CAN connections to the drone instead of just one. I'm not sure why. They don't use the second one for anything, but I think they're planning on doing something with it in the future. Upgraded HERE link. All of the old designs for the Busy Bee were in SketchUp. And so now all of these were sort of remade from scratch in Fusion 360. And as I was putting it together, I was pretty happy with the design mostly, except for I would like maybe a little bit better split between the two. All of the electronics kind of mount to the top plate here, which is actually a pretty nice design. And then the frame and the chassis are kind of the motors and the bottom plate kind of here. So it's pretty good. I think maybe a few more tweaks to really get it split super nicely. I hadn't, as I was putting this together, I realized that I didn't have any notes about what the cable was that's connecting, because we're using different antennas. As it turned out, I was using these old, this antenna upgrade kit, but I wasn't using the antennas because they're really big, but I was using the cable. And so I never had to buy the cable by itself. So the cable that we're looking for the record is MMCX to SMA. It's kind of maddening sometimes how many different connector types there are. It's hard to keep track of them all unless you do the stuff regularly. You know, you do it twice a year, you forget what's what. But anyway, that's why the note in the log here. So the all-up weight for the Busy Bee is 1,492 grams with a 6,000 milliamp hour battery. The equivalent weight there for the Hexoon all up is 1640. So we're looking at about 150 gram savings. That ought to yield something like a 20% extra flight time. Something in the neighborhood. We're essentially getting 1,600 extra milliamp hours for the weight that we're saving. But the design is also a little bit different, so it's probably not going to be exactly like that. But I did fly it outside. I did a hover test. I flew it for about 6 or 7 minutes, and everything went beautifully. So I'm going to take it out to the park and do a real flight with it. And I also don't have a great way to mount the camera on there. I've got an old way to do it that is fine. But I think I can do better than that. So, yep, looking forward to that. And then a lot of stuff on the build project. And again, this is spread out over the last 3 weeks. So I don't have this as well documented as I would like. One of the things that I had done about 3 weeks ago is put together a good little summary of how to do a block sum. So Addison and I had worked on this earlier in the semester. But I've got 1, 2, 3, 4, 5, 6 different ways to do it, all documented on this appendix, which is going to go with the algorithms class. So when we talk about image processing in there, I'm going to stick a bunch of this kind of random junk in there, and then it'll be a nice reference for me as much as anybody. And then it turned out that Xarray has this really great Corson function, which I think Addison has talked about in his lab reports already. But it handles essentially, if it's a geospatial data set, it recalculates its location. So it does more than just sort of a simple block sum. Really nice to have that. So, yep, nice to see that. OSM has a CID polygon, which I discovered when I was on OSM for something else. It's OpenStreetMap. So you can see that the CID is actually on here, which is great. I did download that file and I stuck it in the CID info. I'm not doing anything with it at the moment, but it's nice to have it laying around. I've been pretty into the Facebook segment anything model, which I think I talked about in a lab report some time ago. Essentially the idea of sort of decomposing an image into its different parts, sort of seen as this generalizable problem. So instead of writing something that specifically looks for this or that, you just segment it, and it tries to sort of mirror the way the humans would do it. Some really interesting good results, some definite bad results. But I did find this great little GitHub, huggingface.co place where you can try this out, and you could just upload a video and you could upload an image. So some of the stuff that we've been talking about, just like instead of having to code it, do it, it's just like drag and drop a video and see what happens. And what happened was it works okay, probably not great enough for our purposes, but still pretty neat to see a demo. This is an old note, but we switched the network timing in the CID from precise time to network time. Precise time is a lot better in terms of the timing, but NTP plays a little bit better with the Percept software, and we did not notice any big difference in like the ghosting or each frame not hanging together. So we were pretty happy with that. I spent a lot of time I was trying to make a big push on sort of documenting our best techniques for doing the movement analysis. A lot of us have now worked on this in pieces. I wanted to try to bring all of that stuff together and take another look at it. This is an example of what the hourly logs looking at. When I record the hourly logs, I was using the sum. In some senses, it would probably be better to use the mean, but you can always go from the sum to the mean because you know what the maximum pixel value is. So you can always sort of do it, whether that's an important recoverable or just an extra legwork. I don't really know yet. But this graph of the activity sort of shows the reason why you need to do that. If you don't do it this way, then you get these really weird, like, bad values that show up in the data set. This is the sum of all of the pixels for each hour. It's not really, this is sort of the documenting the sort of naive approach to doing this. We had thought that sort of the variability would sort of just kind of come out in the wash and aggregate it over an hour. It would just work, but it really turns out not to be the case. So this is a plot of activity, 24 hours, 48 hours, 72 hours. So these are by days. You would expect this to be a regular sort of a diurnal cycle, and it's very definitely not. So that tells us that this approach is on the wrong track. This is what you guys had showed from OGIS, although I did notice that one of the days was not recorded in the log properly. So we do have a little bit of work to do, just as an aside, trying to make sure that the missing hours and things like that, and even missing days, are sort of handled correctly in the analysis, just being attentive to make sure that we're not missing something there. So again, I'm going to have to assemble this into a nice format here. But one of the things that I did that was kind of interesting was to take that hourly record and to just look for non-zero pixels. So this is essentially just a plot of whether that pixel turned on at all ever. And the neat thing about this is that it shows really well the movement. So movement dominates here. And the reason that this is interesting is if you just take the raw sum of those pixels, it doesn't work that well because the walls are there all the time. And then the furniture is there some of the time. And you've got to sort of factor that out. And then the movement, which you want, is often very ephemeral. Somebody passes through and they sort of turn that pixel on maybe once. But that's the activity that you care about. So there's this sort of like, the activity that you care about is sort of like actually next to zero. It's above zero, but it's not any of that stuff. You want to kind of focus in on that. So I was looking at ways to sort of isolate this. So this is just any time the pixel was turned on or not. So the neat thing is, because people don't walk in the same spot, right? As one person walks through, the next person walks through in just a slightly different spot. Over the course of that hour, the pattern is that people just turn on all of these pixels. And the spots that are sort of sampled all the time are sort of naturally discounted by this because the wall gets sampled a bunch. It's still in the record, you can still see it, but a lot less than it would be ordinarily. So movement really dominates in this analysis, and you can see the diurnal cycle sort of show up really nicely. That's about as far as I got with that. And I was kind of getting ready to turn the corner on that. One of the things I've got a note on here, I think we're going to need entirely separate strategies for analyzing movement and pause. Like you try to analyze it one way and all you do is you pick up movement, and then basically pause gets squashed out here the same way that it gets squashed out in the walls or the tables or anything, de-emphasized, right? So yeah, maybe difference comparisons are going to be the way to do that. I don't know, but we'll keep working together on that. And the goal is sort of over the next 2 or 3 weeks, really lock that down so that we're done. And we've got a reliable technique that we're happy with. The other big thing is working with the team on the sound work. So I haven't had a chance to report much on this at all. So some of this will get into a little bit of detail, but it was really, really interesting. So I hope you guys will find it as interesting as I did. I know next to nothing about working with sound. So I was, following very closely with Tanner and Brandon from ICAT. Nicole is in math, and she's used to doing movement analysis, and a lot of it based on sound, but not in sort of the way that we're doing it here. So we all had sort of pieces of the puzzle. The gist to this is that we have these like microphones that have an array of 4 microphones. So they're kind of 3 kind of pointed, sort of like pyramid shaped, one pointing at the top and then 3 kind of pointing down at the bottom. And then because there's 4 of them, they kind of can be put together to come up with a directionality of where things are. And there was a format for recording that. It's often really hard to get away from how the data is stored and what you can do with it, right? So it's always good to be attentive to data specification and storage formats and things like this. In this case, they basically take each sound and turn it into 4 channels, an X component, a Y component, a Z component, and a W component, which is like the omni noise, so all of it. And then from that, you can mostly reconstruct the signal by creating what's called a virtual microphone. And you say, all right, I'm interested in the sound from this direction. What does that sound like? And so you give it like an altitude and an elevation angle, and it's like turning your head and kind of looking around and hearing, and then you can kind of focus in on what's over there. The way that the stuff gets recorded is actually pretty interesting. It turns out that a sound file is really just a raster, which I totally wasn't thinking of it that way, but it is. It's basically just like an image. It's an array. It has the number of columns for however many channels you're recording. So in a mono recording, 1 channel, stereo recording 2, in this case 4, and then each row in the channel is an observation at a point in time. And it just samples this at 44,000 times per second, or whatever the sampling rate is. There are different sampling rate. So the array tends to be this like long skinny thing. So you wouldn't plot it in the same way that you would do an image, but the data is essentially much like what we're used to working with. So that was cool. Getting the data in and out, again, was a lot easier than I thought. Nicole had just like dragged a WAV file into MATLAB, and I was like, how does that work? She's like, I don't know, I just drag it in. So I was like, oh, maybe it's that easy in Python, and it is. So from SciPy, you can import WAV file. Wavefile.read reads the file. The rate ends up being like that 44,000. So it's how many samples per second. And then the X is your array. So if you look at the shape of the array, in this case, it's this ambisonic format. So the X, Y, Z, and W channels. So it's 4 columns and then just like a huge number of rows, 44,000 per second. So if you plot a little section of this, you get something that looks like this. You see each of those X, Y, Z, W plotted. And then, what's a little bit different for us is that essentially what we're plotting here is, if you can imagine like a diaphragm, like 3 different diaphragms, one for the X direction, and one for the Y direction, and one for the Z direction. It's recording like the position of that diaphragm as the pressure wave shakes it, right? So it goes up and down and up and down and up and down. So you get these positive and negative intensity values. So pretty neat.
Are the different colors like different directions?
Different, the different channels. So X, Y, Z, and W. And I didn't remember which is which, but yeah.
I think I see 3.
There should be 4. There's an orange one,
okay,
kind of hiding under there.
Fun fact, do you want to know why the most common sample rate is about 44,000?
Yeah.
It's because it has to take at least like 2 for each to know that it went up and down, and most humans can't hear above about 22,000 hertz. So 44.1K captures like the entire human sound range.
Oh, that's interesting. Wow. So if I wanted to capture it for my dog, I would need a much bigger sampling rate.
Yeah. Otherwise, it like distorts when it's higher than that because it doesn't catch that it went up and down.
Yeah. Oh, that's cool.
Hmm.
Cool. Where did you run across this stuff, Rebecca?
I took a couple audio technology classes.
Oh yeah. Here, I suppose.
Yeah.
Oh, did you take it with Tanner or Brandon?
No, I took it with Scotty. I forget his last name. He's one of the music professors.
Okay.
Hannenberg, Dr. Hannenberg.
I'm fascinated by this. I was telling Brandon, like I would love to just sit in on a music technology class. Like there's so much, there's parallels to like image processing, but there's also these really interesting differences and like, yeah, that's really fun. The way that you pull this data back out again then is a little bit tricky. The purpose of this spatial format is sort of, or the use of this is sort of changed with the advent of virtual reality technology. You know, spatialized sound is actually super important. So if you're playing a game and your head moves, you want the sound feeling to move. So the ambisonic format is actually used all the time for that. In this case, what I needed to do was write what they call a virtual mic, or sometimes a panning a source. These are terms that I don't really know very well, so if I'm using them wrong, that's totally possible. But the gist here is you specify an azimuth and an elevation, you give the XYZ angles, and then you have to give it this P parameter that tells you what the shape of the mic is. So that controls basically how much of the XYZ stuff you get. So that's here, and then how much of the omni that you get. And this is actually an error. This should be multiplied by 2.2 to the square root of 2. So this is a mistake, and I'll talk about that in a second. So essentially what you can do is you can say, I want this thing at like azimuth 90, which would be straight up, and elevation 0. And when you're at 90, azimuth is across. So, and it's not really north base, but horizontal angle, and then elevation 0. So not up or down. You just give it the XYZW, and then you know what kind of mic you want, and you get a little array, and then you can just write out the array with whatever the rate is that you were working with, and then the data. So bringing data in and out is super easy. This is the note here about I made a mistake when I divided by square root of 2 instead of multiplied by the square root of 2. This totally does change the waveform. I didn't think that this would matter I didn't think it would matter a lot, because I thought it was sort of like, how much of this signal do I take and how much of that signal do I take? But Tanner explained that because these are all sort of phased, what you get is sort of the ability to cancel out. You know, it's sort of like subtracting the omni from the rest, and that if the waves are matched, then you really do level those things out to like near 0. So getting that multiplier actually really matters a lot for reconstructing the signal properly. So the blue here is the better version of this, and the orange is kind of the mushy one that's not done quite right. And you can totally see that in the signal. The one is much more coherent than the other. You can show the channel over time. So this is just over time. So in this particular sound file, we had Brandon walk around the mic and just count. So 1, 2, 3, 4. So you can see the intensities peaking. And then what I'm trying to do is extract him moving around in space. Question?
I'm just looking at it. I was thinking like if he was saying some numbers loud, I would just count.
Yeah. There should be, I forget how high he got, but 20-ish. And then this is the left and right channels over a bit of that time. So nothing exciting happening here except for, this is at an azimuth. This is at an azimuth of 90. This is the other side of it, an azimuth of 270. And so you can see that the waveforms are different, right? So there's more sound coming from here and less sound coming from there. it's still not perfect. And one of the things is to try to figure out how to do the full spatial reconstruction. I've got, I think, some slides on this, or maybe I don't. But because it's all NumPy, I can basically just give it like a mesh grid of all azimuths and angles, and then I've got a projection that projects it back to Cartesian coordinates. Yeah, I guess I didn't show any of that, but I'll show it next time. This is plenty anyway. I was reviewing a paper, and this paper was talking a little bit about taking a depth map and then normalizing it, and then applying a color map to it for the purposes of sort of like some machine learning. I thought that this was interesting because it was sort of a different way to split like a DEM into 3 channels, and it reminded me of the stuff that we were doing in CID. It is not the same thing, but it's done, I think, for the same reason, which is to apply the extra color information gives the machine learning and the deep learning more to kind of grab onto as it's training. So I just wanted to make a little note of that when we'll see that again when we write the other paper. My last bit here is the other big project is I'm trying to polish off the revision for Sam's paper. So Sam's paper was on detecting using deep learning to automatically classify tornado damage. The revisions are due today. This is at the second round of extensions for me. So I'm really trying hard to get it in. I think I will be able to get it in today. I've got nothing else going on this afternoon. I was going to make a list to show you what these are like. For those of you who haven't yet gotten revisions back on a paper, Gunjan got some back on his. They're often, the scientific reviewing process is this anonymous peer review process where, it depends on whether it's double blind or single blind, but some anonymous reviewers that you will never know probably review your paper and they tell you why it's terrible. People aren't used to getting that blunt of feedback back. Normally in social situations, you're kind of nice about it. Most peer reviews are pretty blunt and to the point. And sometimes they misunderstand things that you've done. And so doing these revisions is often very frustrating. Shashank and Addison will get to the point where they're getting revisions back from me on the work that they've had, and you've done your proposal, and Addison, you're doing your proposal, and getting you guys used to this sense of like it's revision after revision after revision after revision, and it just takes a long time to get everything done. But things really are a lot better. As I'm getting to the end of this process, I'm looking at sort of like figures that they asked me to make or other things that they asked me to do, and I can see that it's a better paper. Like it is definitely better than what it was. And so for as much of a pain in the ass as it is, it is all to the good. Anyway, so that's about all there is for that. I gotta finish that damage paper today. I want to do a proper flight test on the Busy Bee. I need to make a better PDF for the movement and pause analysis and hopefully solve the sound localization problem. And I didn't have this on here, but also worked with Rebecca on splitting the point cloud loader from the classifier. So that's on my to-do list for next week. That's it for me.
Can you guys see the screen still?
Yes. Yeah.
I've got a rather short one today, even though I had the most busiest week over the start of this week. So talking about the summer work I'm doing with Dr. Kim, I finally managed to go through the deep learning process for image segmentation. So for every Google Street View image that a person sees through his commute from home to work, I was trying to see how much green space is he exposed to. So I was using a deep learning model to just factor out the greenness within that image. And this is the original Google Street View. These 4 are the 4 panoramic views that he sees at a particular location. And these on your right are the 4 green segmented images. I was just trying to compute the a ratio of greenness in each view. So that this has been done, and I'm writing everything out to a big pandas data frame. So talking about pandas data frame, I wrote out how like what are the different classes and how like what percentage of those classes were they exposed to. So I've been pretty much with pandas the whole week, and I've been working with a lot. This is a very big database, so I could not do it without the knowledge of pandas. That I'm very sure. Like it would take me like a million years to even look at this data set. And with pandas, it's like pretty easy. Like it's pretty interesting. It's everything is visualizable and it's very nice. So I was able to compute like so on the left, the image you see is different origin destination pairs and the greenness average greenness ratio that the commute is exposed to. So for the 10th origin destination pair, the average greenness is 44 percentage. So this is what it is saying, and from the database of 1046589, I get something like 1000, and this is pretty neat. So pandas all the way. This was a very fun exercise, a very practical exercise. It was fun. I still need to do a little bit more with pandas. I'll probably be finishing up in the next week. I'm just like merging multiple databases and hoping everything sticks together. So that's it.
I may have to get you into one of my classes to talk about, like, I need a second person to say why pandas is so great. Like,
I'll vouch for it.
I find students don't really understand why I'm trying to teach them this stuff, and I'm like, oh no, this will save you $1 million.
Even I did not until I like actually use pandas.
Yeah.
Like such big databases not being like not taking millions of hours to load, and that's completely nice. So the next thing I did was last week I tried on Rooster the deep learning using animations from ArcGIS. What happened was when I reached the trained deep learning model, it just crashed. Whole ArcGIS crashed. So then I decided to come here thinking it was a remote desktop issue, but it was when I did it again, it failed again. So the Rooster just crashes when I do the trained deep learning model situation with the video. The next thing I decided was to do it on my laptop. When I did it on my laptop, I'm 99% sure that I follow the same procedure, but I am getting a few new things. Like when I was doing the extract frames on Rooster, I was kind of getting the same images from the same views, but with my laptop, I'm getting like multiple views which are in the video. So I'm not sure what's going on with that. And I'm again following the procedure of extracting frames, adding them to a mosaic dataset, and then running the deep learning and image classification model. The sad thing about this is I thought it would work, but this is where Rooster crashes. But my laptop did not crash, and the number you see is the name of the folder that has all the images, all the labels, and all the statistics needed for the training. But when I load the folder, it gives me an error. And I think this has something to do with either an update or something, because I did not go through all the errors, but at the end, I see that it says the specified module could not be found. And it's something to do with like a torch Python DLL.
Yeah.
So I still think it's more to do with the update or something. I'm not sure of that.
Yeah, as you were talking about this, I wondered if minor Arc update has broken something. Like I definitely got the deep learning stuff to run for the Roanoke stuff, but maybe that we went from version 3.11 to 3.12 and that broke something. So.
I think that was it. And I also tried to look like update because my laptop has updated ArcGIS, and I was almost sure that it would not work in my laptop, but this had like I think a few versions back from what we have right now, and it's not updated. So I'm not sure what's going on.
Okay.
But I'm like kind of sure that it's still an ArcGIS issue. This is still I think worth some time. I didn't spend too much time on this, but like this was fun. This is still a fun thing I want to do. The next big thing I did was I had to submit a pre-recorded video of presentation to the ASPRS Technical Symposium. So I was able to do it. It took some of my energy looking at myself talking and thinking why I said this and that, but it was a fun time. The slides look really good. Thank you so much, Dr. Mingle, for your help on that.
Thank you.
It was a fun presentation. This might have been like the most like I want to be on time. I want to say these things, and like this presentation was really like good for me. So the major things I finished this week was preparing the presentation for the ASPRS, the deep learning for the summer project. I still have the other things like to be completed. I'll probably work on those like more on the next weeks. And regarding the video annotation tools, I'll probably like choose two of those and like completely try to do the video annotation tools, the tools I'm referring from last week. Yep. So that's it.
When does the ASPRS thing happen?
So the ASPRS conference is from 12 to 15,
Okay.
and we've got the last slot, 15th, on the 15th, from 2:30 to 3.
Okay. Thanks.
Stop the sharing and anyway, let's get the next.
I have to enable screen share for that.
Rebecca, do you want to go next?
Sure. Okay, so I did a couple random things this week. First off, I showed you all 2 weeks ago, I think, the like rotation thingies. It didn't work perfectly, and I was trying to figure out why. So I was like isolating the different axes, and like the y-axis rotation worked really well. The x-axis worked like kind of okay, and the z-axis was just doing y-axis again, and I couldn't figure out why. Then turns out it was about Euler angles and gimbal lock. I don't know how much. It seems like Dr. Pingle's encountered this before, but I don't know about the rest of you. I had not. But apparently, the Euler angles, each axis becomes like a local axis. So when you rotate the x-axis, then it's doing the rest of the rotations based on that already rotated axis. So pretty much if you put one axis 90 degrees all the way, then the rest of them, like, it can only rotate in 2 dimensions instead of 3. So because we had rotated the point cloud from being like this to being like this, that was an x-axis rotation 90 degrees, it couldn't do, like, the y and z became the same. So I'll probably tinker about having to fix this, but honestly I was thinking like I don't even know how much we need a z-axis rotation. Like I don't know how much we're gonna need to like tilt the point cloud like that. So worst case I just get rid of it.
Yeah, that's a good thought. It might be better not to have it. You could wind up getting it misaligned, would be unpleasant. I've experienced that before for sure.
Yeah, I feel like maybe like rotating it like this would probably be helpful, but not really any other direction that much.
Yeah.
At least not like with your hands. I don't know.
Yep.
Then I looked into the 3D tiles, which would be really cool. Turns out, you need an API to even access it, which is like a normal thing, but then it's kind of a whole complicated process to get an API key, and the whole thing is all very experimental. But I did look into its example for loading a 3D tiles from the Google thing, and then on the right is the New York Times 3D loader we have, and like I don't see a one-to-one like plug and play kind of correlation, but that also doesn't mean it doesn't exist, because I still don't really know how it works. It's very complicated. Could be possible, but I don't really know how.
Huh. Okay. That's super good. I think maybe I do see how this could go together.
I mean, that could be like this await load thing, like that's probably where it would go, but I don't have 100% confidence that they're the exact same thing.
I think we should just be able to specify this straight in the A-frame side. If all you need to do is provide this URL with your API key embedded in it,
Yeah.
I think it might work.
Yeah, I mean, it might work. Yeah, there's like, I don't know, I would say like 90% chance it might work.
Yeah.
But who knows? So yeah, it could be worth a try if we want to get an API key up and running.
Yeah, let's one or both of us can do it. If I
Okay.
there's still I'm still really interested. I think that this has the potential to like really enhance the the point cloud classifier, because you'd be able to like overlay a 3D model on top of it, right? I don't know.
That would be really cool.
I think it would be really cool.
Because then you'd be able to exactly tell what you're doing, especially if they lined up, which might be more difficult than, but could work.
Yeah.
And that's also assuming that both of these can load at the same time, which like I'm pretty sure would work. But I just tend not to believe that things will happen until I see them happen. And then I also worked on a new UI.
Oh, that looks good.
Yeah, I don't know about the buttons. Like, I could change them, but they're like radio inputs versus buttons, which are like different things. And I just had to like redo the function, which I don't really want to do right now. But I might do today. I didn't want to do it yesterday though.
This looks super good. Thanks for doing that.
Yeah, and the point size thing doesn't actually hook up yet, but maybe that shouldn't be too hard.
Yeah.
Okay.
The coloring, you could do the coloring maybe a little bit like you've got. Like I really love the design of your classification buttons. Coloring could kind of be the same. Similar kind of a neat design.
Yeah, the coloring's supposed to be like taking up this space like this, but I don't know what the grid's just not working the way I wanted it to, and I can't figure out why yet. But it's probably like one typo or something somewhere. CSS. So yeah, I'm gonna clean that up, make it work a little bit, and then also try to implement the super hands. I looked at it, and I'm thinking like making a copy of one of the glitch things and doing that, and then trying to test them side by side to see which one works nicer.
Cool.
Okay.
All right, nicely done. Thank you.
I will go ahead and share mine. Yeah, so I have a short one this week. I am currently at the beach with my family, so I've been working when I can, but also taking a little bit of time off.
For sure.
So mainly what I've been doing is some of the space-time cube stuff with the daily summary data, and then a little bit of work on the like proposal side of things. So with the space-time cube, I have a fully working space-time cube with the daily summaries now. So previously I was having these projection issues. So I went into Python and had the projection to be WGS 1984. So right now, since I have it set to 19 like WGS, it currently thinks that like the 1x1 meter grid is actually a 1x1 degree grid. But that's expected. This was just kind of like a trial run. So rather than trying to project it perfectly onto the Earth's surface, like where it actually should be, more so just saying, can I just put a projection on it so that I can then do like the analysis that ArcGIS wants me to do with it. So it's fixed, but like not actually correct. So I'm still having rendering issues with the space-time cube in Arc, which is surprising to me because I was working on Rooster as well when I was doing this. And I think it's somewhere around 57 by 40 in the X and Y directions. And then there's 249 days of like times, like daily summary timestamps. So that comes around 570,000 values, which maybe that's still too many, which I just felt was a little surprising. But then with the hot and cold spots, because visualizing like the space-time cube in 3D was still a bit of a challenge. But being able to look at like the hot and cold spots was not as difficult. So they're mostly hotspots and they're in like the stairs in the central areas. I couldn't find where I put my screenshots for these when I went to make my lab report this morning. So unfortunately, I don't have any pictures of it for now. But I will include them in next week's. And then, so moving on to like proposal work, I'm kind of working on still deciding like a concrete topic. So like two of the ones that I think Dr. Pingler and I have been talking about recently have been the like material resources angle, and then also kind of looking at like creative collisions and seeing like how can we measure movement and pause and like things like that using these LiDAR sensors and like the tools that we do have. So with the material resources, I think that we found that like it seems like a pretty feasible topic in terms of like we can define what we want to look at, we can define how we want to approach it, things like that. But it's not necessarily the most attention grabbing material. It seems pretty obvious that like use of a building is going to be clustered around where the things are inside the building. So it definitely doesn't seem necessarily the most insightful or groundbreaking topic by any means, but it's still an angle. And then one of the other ones that we've been kind of talking about were kind of looking at creative collisions. So that would be a little bit more interesting and to say like, you know, how can we measure these impactful things that are happening between two people using this like quantitative analysis instead of just like, you know, using purely qualitative to kind of measure like meaning and things like that. So it might be difficult to measure these sorts of things. So my general thoughts as to how that could happen would be using percept data to see like how can we look at like the timestamps within percept data and say if this object is moving with this velocity at this point, and then it slows down to almost a standstill for like a couple seconds and then keeps moving again. What happened during those couple seconds? Was there another object at the same time that did the same thing? To see like, was there an interaction between these two like percept objects? So that would be kind of one way to think of maybe that's a way in which we could track those sorts of things. One thing that I do want to do either next week or in a couple weeks or whatever, is go over to the CID building and just like mimic a couple of those. So Shashank, I might have to borrow you for that one day. But just like going over and you're walking down the stairs and I'm walking down the hallway and then like we run into each other, we have a quick conversation and then we like keep going about our ways, and just to see like what does that look like on the percept data? What does it look like on the raw data? How can we kind of like what sort of things stand out so that we can then measure that like, yes, this is happening. And then in the future, how can we say like, can we apply that like similar technique that we saw with our collision to, I guess, other collisions? How can we like isolate the collisions themselves? And then some of the other proposal work was kind of working on like what data source is going to be like the kind of primary data source for doing this sort of analysis. So obviously there's the percept side of things, and then there's also the raw image side of things. Percept, from the couple months of experience that like I do have working with percept in the raw data, I found percept to be generally a little easier to work with. The vector data format is just like, it's a little bit more easy to manipulate and move, and like you can make selections on it. And then additionally with percept, furniture and walls are like not really going to be a major issue. They'll probably never be an issue. But then percept does have its drawbacks, which are like, one, there's a ton of noise that has to be dealt with and accounted for. And while we've worked on fine tuning that, and I do think that changing some of the parameters that we have changed are a lot better, noise is still going to be an issue. And then one of the other issues with percept is that you can like lose track of temporary like non-moving objects. So we had done this where like if you're sitting down at a spot for more than like 15 seconds and you're not moving significantly, it will drop you as an object, and then we'll only pick you up again when you start moving again. So even if an object becomes like undetected, or like an object drops from the sensors for like, can be 1/100 of a second, as long as it drops, when it gets re-rendered as a new object and not the same object. So that could also cause issues of like if one person does end up walking down a hallway and having an interaction with someone, there's the line in which they were walking and it gets broken into two lines and you don't even recognize that it's not actually two different people anymore. It's just one object that got marked twice, basically. So those are some of like Percept's kind of downsides. The raw data, on the other hand, I think is generally a little bit more difficult to work with. There's a lot of projecting and pre-processing and resampling within Python that like has to happen before that data is like fully usable. And then even once that has been done, there's still kind of issues with like furniture and walls and how do we resample around furniture? Should we try to cut out the furniture before we resample the data? And then what happens when the furniture moves? And like there's lots of these kind of pieces within the data processing itself that becomes a little bit more difficult. But one of the advantages is that one, it's the raw data itself, so it's not just like what the algorithm is already picking out. We can actually look at it and say, here's what's happening within this data, or more so just like seeing what's actually going on. And then also that data is like perfectly regular intervals with time to the exact second. We can say this is what happened at this second, this is what happened at the next second. And we can make like a lot of decisions based on that. So they both have their advantages and their disadvantages. So I kind of want to figure out which one I want to end up working with.
This is a good list, and I really like the color coding. I had another one that I thought of yesterday, which was the Percept data. You know, you kind of have the system and it runs and it records the data, but there's no ability to go back. Like it kind of is what it is. Whereas the raw data, you've got the potential to like, all right, we can change it around. It's more flexibility in the analysis. So not sure how to write that up exactly, but.
Something like that.
Yeah.
Yeah. So that's all I have for this week. Next week, I think either next week or the week after, meet with Dr. Pingle and then also maybe Dr. Baird and kind of work on deciding like a main thesis topic. And just seeing like what we think will be feasible, what we think will be interesting. And then also at some point going over to the CID and kind of just like emulating a creative collision to see what does it look like? How can we kind of measure these? How can we isolate them just to see like, is this a feasible thing that we can do before trying to maybe jump into it as like a thesis, for example?
Cool. That's great. Thanks, Addison.
Yeah, of course.
Cool. All right. Well, thanks everybody for coming in on a summer Friday. I find it kind of nice to come in this morning and hang out for another hour on this. It's a nice bookend to the week. And we'll have a nice weekend. We'll see you next week. Bye, everybody.
Bye bye.